for coming. Thank you, Miguel, for accepting our invitation. So today we have Miguel Correia, who's going to be talking to us about non-perturbative uses of Feynman diagram from hydrogen atom to black hole. So please take it away, Miguel.
Thank you. That's an amazing intro. Okay, so yeah, so the main question, like one of the marquee questions I want to address today is, well, let me just say it out loud, is where is the hydrogen spectrum hidden inside the S matrix, or where is the black hole quasi-normal modes hidden inside the S matrix, and how can we get to them using Feynman diagrams? Okay, so I think it's important to start. So I'm going to start talking about these three scales. So I consider 2 to 2 scattering. Okay, so 2 to 2 scattering of two bodies going into two other bodies. And in this scattering system, there are 3 kinematic scales. Okay, there are 3 kinematic scales. Well, one is very obvious, is the impact parameter. Okay, so this is the distance between the 2 particles. Okay, B, the typical distance between these 2 particles. Then there's another kinematic scale, which is the wavelength in the center of mass, so the wavelength of these particles. So here I talk about lambda, I call this lambda, and I call this is the usual de Broglie relation, h bar over the momentum, and this is the center of mass momentum, which is the same for both. And of course, if the particle is massless, so then this p is h bar times some omega, some frequency. So these guys, okay, but let me branch out. I can call this lambda. You can still see here at the bottom. This lambda has 2 possibilities. One is the lambda de Broglie if the particles are massive, or it's just 1 over the frequency of a classical wave of a wave. If the particle is massless, this could be just the wavelength of that wave, right? And oh, sorry, by the way, I should say that you should stop me if you don't understand anything. I prefer if you ask immediately and then like save the questions after 1 hour. So the other thing is so all of these 2 scales are there. So this one is only there in classical mechanics, impact parameter. This one is there in quantum mechanics. And then the third one I'm going to show is only present in QFT, which is the Compton wavelength. And the Compton wavelength is just given by lambda c h bar over m, where m is just any mass that can appear in the QFT. It can be the mass of these particles, or can be some mass of some virtual particle that is not immediately like it's not a state that you're scattering, but it can appear in the QFT. So this Compton wavelength matters in that context. So in terms of pictures, I can just draw a simple figure that captures all these wavelengths. So I basically have one particle that comes in with some momentum p. It has some wavelength, then it scatters. And then I have the mirror process because we are in the center of mass. So I have something that I have the other particle with some wavelength, then it scatters. Okay, so this would be the lambda I'm talking about. So this would be p, right? This direction. So this is the lambda here. And then they have some distance, b. And then let's say they interact, right? They have some interaction. And they interact, they exchange sometimes, for example, a photon, a virtual photon. But then I can have loops Like I can have exchange of virtual particles which are massive, and these virtual particles I can consider some kind of loop diagram, and then they, for example, this could be a electron positron pair, and these virtual particles have some content wavelength of their own, okay, for example. So this picture encapsulates all these kinematic scales. So this discussion is good because I didn't have to introduce any coupling, so any strength. So this could apply, all these kinematics apply to QED, to gravity, any system, right? And now what I'm gonna talk about is, for example, in the hydrogen atom, we want to consider some. I want to consider the case the impact parameter and the wavelength of the particle is much bigger than the Compton wavelength, because the hydrogen atom there's no QFT effects, and then we can talk about how the Feynman diagrams look in that case, and if there is some. And so this is what I'm going to do now. But I'm just going to write down now a table between all these different regimes. So is there any question here at this point?
Yeah, looks like there's not.
Okay. So very well. Yeah. Okay. So
the two quantities that you wrote, Miguel, the
Yeah.
first two quantities are quantities that you can vary when you do an experiment. They are what we really kinematic quantities, like S and T, you replace by V. The
Yeah,
third
exactly.
is like a characteristic of the system, right? The quantum wavelength is not something you vary in an experiment.
Yeah, exactly. That's a good point. Yeah. So there's nothing I cannot control the Compton wavelength. It's only that it's a property of my theory, like the masses of my particles, and so this one I cannot control. What I can do is make the other ones much bigger compared to that one. So in the sense I can control the ratio.
Right.
So okay, let's do this table here. So yeah, one thing that I'm going to focus here, like, so for now, just to disable this table. So now what we're going to do is consider the case in which I want to suppress QFT effects. I want to consider my particles far away enough that all of these massive exchanges are suppressed. So I want to take the case where B is much larger than the lambda quantum. So basically, the particles are very far away, and just these virtual exchanges do not play a role. Okay, and once you do this, then you can play with the other. You can play with the other lambda, which is the lambda de Broglie, or the wavelength of the particles, and then you can consider ratios, and you have four possible cases. So one is the mass. So if the masses are different than 0, okay. So if both particles are massive, and the other is when one of them is massless, okay. And so what I can do is here at the top. So here at the top, what I do is I consider B much larger than the lambda de Broglie, or lambda, okay. In this case would be literally lambda. In this case would be just the wavelength of the massless wave. And of course, I'm in these conditions, so B is bigger than both lambda de Broglie and lambda Compton. So in this case, I'm taking the impact parameter also much bigger than the size of the wave packet. So that means I'm just going to end up in a classical regime. So this would be just classical mechanics. So for example, I would be just this would describe the scattering of 2-point particles going around each other. Okay, and for example, one application of this would be for today it would be like when we observe binaries. black hole binaries, this would be the inspiral stage, right? This would be at the inspiral stage where the black holes are very separated. I can treat them as point particles. So in principle, if I take this regime in my QFT, I should be able to describe something like the inspiral stage of black hole binaries. Okay, and now in this case, in the case of massless, this lambda is just the wavelength of the massless wave. So in this regime, this is what people call typically geometric optics. And this would, for example, describe the bending of light around the sun. So I have one object, which is massive, and then I have a null geodesic that gets deflected. Okay, so this is all classical, purely classical, right? Now, this area here is typically called what people call iconal regime. Another name for this, iconal regime. Okay, is there any questions here at this point?
I'm a bit confused. Can I
Okay.
just ask a question?
Yeah.
Usually, it's a matter of working instead or in S and T, Mandelstam.
Yes.
Usually, the iconal, if I remember correctly, is like high energy, but forward scattering is zero angle. That's iconal.
So iconal is yeah. So exactly. So everything that I'm talking about here will translate into what you're saying. So for example,
but I thought then it looked like if it was classical, the angle doesn't need to be zero, the scattering angle, right?
Yeah, exactly.
That's what confused
that's a good point. That's a good point. When people, yeah, exactly. So iconal people, yeah, exactly. So you can, yeah, you're right. So people, I think many times when they mean iconal, they really mean that the scattering angle is small and it decays with the disk. So it's really like taking B. So usually when people mean iconal, they take B to be the largest scale. So even bigger than any like dynamical scale, which I have not introduced. So if I take B much larger than the Schwarzschild radius, then the scattering angle will be very small. But I haven't introduced yet that scale. So the usual, let's say, this is the iconal in terms of kinematic scales and allows me to describe also finite scattering angle with these scales. But if I add additionally that this is also bigger than the Schwarzschild radius, which is 2 times GMM, then this will be really what you're saying, that the scattering angle will be very small. Yeah, good question. Yeah. But since I want to do something very generic, this is all the skills I have available for now.
Fine.
Okay, so then the other the other regime classifies into this we call Born, or let's say a wave regime. Maybe the purple is a bit hard to see.
I think it's fine.
Yeah. So what I can do now is, instead of making B much larger than lambda de Broglie, is to make B of the same size of lambda de Broglie much bigger than the content, right? So I can do B of the same order of lambda dB, but much bigger than lambda content. And just this relation here, so this guy, if you remember, this is h bar over T, much bigger than h bar over the mass. So this implies that the momentum is much smaller than the mass. So it's a bit small already. Maybe I have to make it bigger. Yeah, so this relation here implies that the momentum is much smaller than the mass. So this implies a non-relativistic regime. So, and the fact that the B is of the same order of the lambda de Broglie, this just means that you are just going to end up in quantum mechanics, right? So this will be wonderful. Quantum mechanics. So this, for example, let me just draw a picture. This would be like the typical picture for the hydrogen atom, right? I have a bunch of a bunch of orbits. So this would be, for example, the hydrogen atom. Okay, so finally, we have a fourth possibility, which is in the massless case. I have that the impact parameter of these objects is of the same order of the wavelength. So one particle is massless, so it's basically a classical wave. It's like, for example, a gravity wave. And I say that the impact parameter, the distance, the typical distance between this wave and the black hole or the massive body is of the same order as the wavelength. So, and again, this is much bigger than the Compton wavelength, so you suppress these QFT effects. And this will just be classical wave mechanics. Classical. And for example, this would be exactly a scattering of a gravitational wave on a massive body. So I have some wave here that scatters. And going back to this analogy with the black hole binaries, this would be, for example, relevant in the ring down stage. Okay. So yeah, are there questions here? Or
what do you mean by this ring down stage? I'm not familiar with this term.
Sorry, yeah, maybe I should talk about this. So when let me just say that when you have the black hole in spirals, the binary, so the black hole starts very far apart, right? So they start spiraling in each other, against each other, and so this is the inspiral stage, where you have basically 2 point particles that are just inspiraling against each other. They emit gravitational waves very slowly, so they slowly get closer to each other, and then at some point they merge. So the merger, you see in the gravitational signal, you see something constant, and then it suddenly peaks a bit when they get closer. They merge, you have like a peak, a burst, which people call the merger. And after that, after they merge, the black hole, there's one black hole because they fuse, but the black hole is still kind of oscillating, right? So it's kind of, the black hole is still going to rest. So this oscillation people call the ring down. And this final oscillation is the final signal, part of the signal you see, which is when the gravitational wave signal kind of gets damped exponentially. So it starts with something constant, the inspiral, it peaks, and then it just has some exponential damping, which is this is what people call these quasi-normal modes of the wave on top of the black hole. So that's kind of. So you see the 2 regimes are exactly like this. So in this one, I have some classical mechanics description, in spiral, and then in this case, I basically just have, well, more appropriately for the ring down, would be some kind of black hole, which is a bit excited and emits some gravitational waves. Like it's kind of oscillating, and yeah.
Yeah. So and where is the scattering here? What is B?
Yeah, so you could say that indeed there is no scattering, and that's the question we're gonna get to, which is like this guy. There's no scattering. There's no guy coming at infinity, right?
Sure.
Good question. Why am I talking about scattering? I'm just talking about the wave that is emitted by the own black hole going out. Okay. So in principle, scattering theory should not tell you how to describe this system, but it does. So that's the point of the talk is that it does. Because S matrices have beautiful properties in the complex plane, which allow you to analytically continue in energies and frequencies, and allow you to access regimes. For example, even the hydrogen atom. The hydrogen atom is not scattering, right? The atom is inside, right? It's bound. So why should I be able to describe them with Feynman diagrams? So that's exactly the point of the talk.
Okay, thanks.
Oh, I forgot to say something, which is in this iconal regime, and this is important, yeah. So there's a critical thing. So if in my main object in a scattering computation in QFT is the scattering amplitude. just to be. So this is some object which tells me the probability of scattering. And then I have two regimes here. Right? I have the iconal regime or point particle regime, and then I have the Born or wave regime. And the point is what we want to say, and it's what people observe, even though I don't think there's a general proof, is that the amplitude in this regime, it exponentiates. So this equal regime, you can say it as literally sending h bar to 0. So all the Compton wavelength goes to 0, the de Broglie wavelength goes to 0, and I just have like a long impact perimeter. So in this regime, the amplitude it exponentiates in terms of some classical action. So this is what you expect from QFT, and this is what people observe. Okay, so there's some kind of exponentiation, and in this case, once I read off this exponent, I can compute classical observables by comparing this formula. Like if I compute the Feynman diagrams and I see that they exponentiate, then I can try to extract this classical action, and then I can compute classical observables like the scattering angle or the time delay, stuff like that. So this just I should see these as some observations, right? And in this case, the reason why we call Born is because in this case, the amplitude takes some form of some geometric series. Well, you should see there's some kind of operator, right? So there's some kind of convolution, there's a Green's function, and this goes to some sort of Born series, a geometric series that you are familiar from. From quantum mechanics, and this is, I mean, this form. So this potential would be some potential, which, for example, would be would depend on the coupling, and if you send the coupling to 0, it's 0, and yeah. So when you write the amplitude in this way, or when you observe that it takes this form, typically you'd associate some kind of wave equation to it. So there's some sort of wave equation associated to this problem, which is exactly what you'd expect. In this regime, you would expect that things behave like waves and all that. Okay. Okay. So with this, let me try to get to this. Let me try to show these properties that we see some examples. Okay. So let's do the hydrogen atom from QED. So the hydrogen atom, I want to consider that regime I mentioned, which is the quantum mechanics regime, which is that the B is of the same order of this lambda de Broglie, much bigger than the lambda Compton. So now this amplitude is a function of two variables. We call it P and Q, or in terms of the Mandelstam invariance, for those that are familiar, just S and T. Okay. And so the process, like the kinematics, can be represented like this. So I have some P in the center of mass, and I have some minus P, and I have some P prime, and some minus P prime. And I know that in the center of mass, P is equal to modulus P prime. But then the difference gives me the scattering angle. So the difference I call this Q, which is P prime minus P. Okay, and Q squared is related to T, so T is just Q squared minus Q squared. And S is the total center of mass energy. So S would be the center of mass energy, which is related to P. Okay. So now this B, the definition related. So if we want, now I want to relate to these kinematic scales. So P is associated with the lambda de Broglie. So lambda dB is just so lambda dB was just 1 over P. So I set the H bar to 1, right? And now B is a conjugate. Typical B is what we mean by the conjugate variable to Q. Okay, so that's how these scales relate. Okay. So if I have a very big, I have a very small momentum exchange, so these particles barely deflect, means they are far away. So if I want B around B dB, so this relation is much bigger than lambda c, what this implies in terms of these momentum scales, it just means that this implies that Q is of the same order of P, much smaller than M. So now all I have to do is take this, compute all Feynman diagrams in QED, and apply this regime, and then see what I get. Do I get something that looks like the hydrogen atom, or there's some hint that we're getting close to some sort of hydrogen atom or spectrum, or if we can see some sort of spectrum there. Okay, so I'm not gonna do all the calculations, of course. So let me just tell you the results. So what do you do? So the first, so let me erase. So these, when you compute Feynman diagrams, there's going to be, so let's say these, let's do colors actually. So let's say this guy is usually it would be red and blue, but I don't have red and blue. So let's say this is the electron. This is the proton. And they have opposite charges, as we all know. So then I have the first Feynman diagram I can write is this one. And they exchange some photon. Then I have this, right? Let's draw it with these lines like this. And this is equal to, if the charge is E, this is minus E squared over Q. Actually, it's just a plus here. So this is the answer. And then if you do a Fourier transform, if you Fourier transform this guy, so you do D3Q e to the I Q dot R, you're going to find something like E squared minus R over R. You're going to find the Coulomb potential. Okay? So far, so good. Then you go next order, and then you see that the next diagram that matters is this one. It's going to be a box diagram. Okay. Now, if you compute this diagram, this regime, which is not very hard, it's a loop diagram, but in this regime it becomes simple. You get something like this. I can write the answer in terms of some I, alpha E squared. So actually, let me write it like this. E squared over Q squared. Alpha E, and then some log at the logarithm. Log of Q squared. So then you can keep going. So what is alpha E? Alpha E is E squared over root of 2 over the mass of the electron. Okay, so I'm taking the electron to be much more light compared to the proton, as usual. Okay. So the reason why you write alpha E is because this is going to be the effective coupling in this expansion.
Yeah,
So,
just to confirm one thing, if I'm not wrong. The first diagram that you have a single photon exchange,
Yeah.
If you do this analysis and then Fourier transform, you get more than the Coulomb potential. This is just in the classical limit.
Yeah, this is the, well, no, if you just take this Q and you do,
But single photon exchange, I think it's just like the component is 0, of the propagator. That
yeah,
gives you
sorry,
the
sorry, this is
potential.
yeah,
There is
yeah, right. You're right. This is already in the
there's
class.
magnetic effects and so on that are relativistic. I think you're taking some non-relativistic things, something.
Yeah, this is already in this regime. Yeah, there are some numerators here usually that survive in the that are
Okay.
in this limit. It's just this.
Fine,
Yeah.
fine.
That one is there's no approximation in this step. Approximation is already writing this. Yeah.
Yes,
You're right.
yes.
Yes. So that's why I think simplify. Also, the formula for this box diagram, which is a one loop, is just simple. It's just this in this regime. I take Q much smaller than the mass. So you see, if there was some relativistic factor, it would depend on the mass of the electron in the numerator typically. But with this hierarchy, it drops out.
Okay.
Yeah, I'm not writing those factors. Yeah. So let me just do the last. The third step. I mean, there are more diagrams here, and then I'm going to consider them when we talk about the positronium. But and in this case, there's another one. So there's a plus, another one which is the triple case, and the structure is the same. Going to be some e squared over q squared, and then now some alpha squared log squared. It's a bit small, maybe. But you basically get more powers of this combination: alpha squared, log squared, alpha cube, log cube. And so all the diagrams become just these type of ladder diagrams. So the full amplitude will be a sum of all of these ladder diagrams. So it's going to be this plus similar one plus similar one. So, and you just keep adding, right? So what happens when you do this? What is the form of the amplitude when you take all these series and you resum? So if I resum and I see what I look at where it converges, it resums to something. Okay, let me give you the answer. So this sum resums to. So this resums to the following formula. Okay. So actually, let me actually write everything. So it gives e squared q squared, and then there's some so there's some IR divergences which you have to regulate. Is the usual story. You have t. And then this exponentiates to some e to the I alpha, some I alpha e. And then there's some gamma functions you get. Again, the alpha e, let me remind you, I wrote so this is just e squared over and so this is the formula we get. After you resum all these diagrams, this is what you find. Okay. So what do we have here? So this is a very interesting formula. So if you take this formula and you square it, all these pieces drop out. These pieces will cancel each other because it's imaginary. This guy will also cancel out, and you get the Rutherford cross section as you expect. But the amplitude is very interesting because the amplitude has interesting properties here. Okay, so if the amplitude is a function of the energy, not Q. Now this alpha E. So this gamma function, this gamma function has poles whenever the argument is a negative integer. So gamma z is it blows up when Z is equal to minus N. Actually, N can be 0, so maybe I can do +1. So N is like goes from 1, 2, 3, 4. That's poles, right? But if I look at this expression, well, it's never real for energies positive, so there's no poles. But if I take the energies to be negative, this alpha E, there's a square root. So this square root of energy will cancel out. We'll give you an imaginary part which cancels this imaginary part, and the argument becomes real. So what happens is that this alpha E, so this square root of the energy goes to I square root of minus E. Okay, which cancels this I. So then you get the following condition. Okay, so poles. Yeah, I'm sure most of you already heard this story, but for those that haven't, so poles come when the argument is some negative integer. So when I replace, I'm going to get some E squared, square root of minus D, minus E over ME equal to minus N plus 1. Okay, so this cancels. And then when you solve, you're going to find some formula. Is the energy. At these values of the energy, you find some poles. Okay, so this is precisely the energy levels of the hydrogen atom, right? So you should recognize this formula. Okay, so this was just to show that from resumming Feynman diagrams, which is purely scattering, right? I was able to retrieve some information about the bound states, right? Which is not scattering, right? And the whole point is that the S matrix, this amplitude is an analytic function of the energy, and it should be able to describe many different processes in different regimes, okay? So if I draw in the complex plane, what we found so there's a complex plane. And so this formula, it had some branch cut. So it was imaginary. Clearly, it was imaginary for energies positive. So there was this. It depended on these gammas, right? Plus I alpha E. So minus alpha E. So this alpha E clearly has an imaginary part when the energy is positive, right? So this is scattering regime. It's positive. And then it had some poles. When I took the energy to be negative, we need to cancel this I, but then give some pole to this gamma. And this would exactly be some kind of poles here, another one here, and then they accumulate here. And this is the minus 13.6 electron volt. Okay. Yeah. Are there questions here?
No, you could carry on.
Okay, yeah, so this is all very basic. So let's do something more interesting.
Turns out there is a question after all.
We have this accumulation of an infinite number of poles as we approach the energy to 0, right?
Yeah.
Is this related to the infrared divergence distribution?
No, this is just the fact that the like when you take the energy, like the hydrogen spectrum is this band, right? And then it accumulates.
Mm-hmm.
Or yes. This accumulation is just a continuum that you see in classical mechanics for classical orbits. When
yes,
you go,
I was imagining like from jumping to one level to another, just giving a photon with infinitely less energy, and that's why I thought this accumulation could have some divergence associated.
Yeah, I don't know. Maybe there's a connection between IR divergence and this like continuum of. I mean, because yeah, I mean the force is long distance. Maybe it's related to that. The fact that you have a continuum. Indeed, this accumulation we do not see it in QCD. Like the meson spectrum is like is linear. It never doesn't seem to accumulate. But yeah. Yeah, I don't know. Yeah, I don't know if there's some, maybe there's some relation. I don't know. But yeah, I mean, this kind of feature is also you see in metals, right? These bands, they get all up. Yeah, I guess if the box is very large, the difference would be very fine. So I guess it's about the distance of the interaction, the range of the interaction, essentially. Because the photon is long range, is infinite, you get just a very fine band as if you have a box which becomes very large, for example. Yeah, maybe there's some relation indeed. And we know that this long range effect is what's responsible for IR divergences. So you're probably right.
Yeah.
Okay, so so another object that is interesting to consider is this partial wave. So this is the last definition I'll introduce. So there's this S of J, which we trade. So the amplitude depends on energy and Q, right? Or cosine of the angle. So this depends on the cosine of the angle. I can trade this dependence on the angle by a dependence on the angular momentum. Actually, let me call it L. Sorry, better L. And this S of L, there's some formula which integrates over the Legendre polynomial over the amplitude. So I'm being very Q, the energy. I'm being very I mean, it's not being very precise here, right? So you just project into angular momentum definite states. So when you do that with this object, with the amplitude of the hydrogen atom, you find this formula. Gamma 1 plus L minus I alpha E, gamma 1 plus L plus I alpha E. So this just tells you a similar story that this guy develops a pole when you have a minus, this is minus integer, and this just tells you, for example, that for a given angular momentum, the poles only start after some point. So we know the orbitals, right? Like you have 1s, you have 2s, 2p. So at the energy level n equals 2 only is accessible when you have at least, when L is 1, the lowest bound state you can have is already the 2p orbital, which is not the ground state. So this tells you this relation. Okay, but this formula will be very interesting when we take now this classical limit. Okay. So are there questions here? Oh, I'm running a bit late. Yeah, I mean, I wanted to talk about this classical limit here. Let me just say quickly, and then move on to a more interesting case where I consider QFT. So if I want to describe a classical scattering process or a classical object, so I want to take, as I said, I want to take this hierarchy where B now is much bigger than lambda de Broglie, right? Because at this stage they are similar. So B, if I relate this B and this lambda de Broglie is like 1 is h bar over P, right? So BP is much bigger than h bar. So BP is just the angular momentum. What is the classical angular momentum, right? So this classical limit means that the angular momentum is much bigger than h bar. And the relation between this small l, which is an integer, and this big L is simply L, big L is just L h bar. So if I want to take this guy much bigger than h bar, I have to take L very large. So what I can do is replace here L over h bar. And this alpha E, in fact, this formula which I keep writing is E squared over square root of energy, basically, but it also has an h bar in it. Okay, so this guy, let me put it back. So this guy depends on h bar. So now the classical limit means taking h bar to 0 of this expression. And when you do it, you find something very cool, which is the following. Let me just show you the answer. So when you take h bar to 0, you find it exponentiates to some classical action. You find E I over h bar as classical, which depends on the energy and on the angular momentum. And the formula for this action is the following. So this formula, this action, it has some interesting formula. Okay, there's some logarithm L squared plus alpha E plus 1 minus L over alpha E, some arc tangent alpha E. Okay, this is the formula. Now, this is what you get from solving the Coulomb problem in the classical mechanics. You solve it using this Hamilton Jacobi method, and this tells you an action in terms of the energies, the conserved quantities, and then all the observables you get from taking derivatives with respect to this classical action. If I take derivative with respect to the angular momentum, I get the scattering angle, for example. If I take derivative with respect to the energy, I get, for example, the period or the time delay. Okay? Now, the interesting thing here from this estimated perspective is that you get this log here. So this log, it has a branch cut, right? There's a branch cut when this log, when the argument is negative. So if I look at this case, okay, when the argument is negative, it tells me a condition that, so it tells me that e to the 4 over e is negative. Okay. So if I solve for this, so it's a bit messy, the blackboard. I try to fix it. So when you solve for this relation, it tells you that the energy is bigger than me e to the 4 over L squared. There's a branch cut. Okay, so what happens in this classical limit is that there's another branch cut to the left. Okay, and what happens is that these poles condense to create a branch cut, and you have another branch point exactly at this position, and this energy you might recognize is exactly the energy for a circular orbit. So then you find the circular orbit here, and then you find an elliptic orbit here, and then when you go to the right, so this is negative energy, and when you go to the right, you find some scattering orbits. Okay. And this property that somehow the classical action for scattering and the classical action for bound, which when you continue this and you get some imaginary part from this, the fact that you get the same actions from a linear continuation was only discovered a few years ago. Even though we've been playing with classical mechanics, as far as I know, it was only discovered a few years ago that both problems are connected by some analytic continuation. And this was only discovered, in my perspective, because we know that there is an amplitude, which is analytic, which exponentiates to this object. So the analyticity of the amplitude tells you that, in fact, you should be able to describe all regimes with the same function, that there's some analyticity hidden in this function. Okay? And indeed, if you continue this guy, so let me just say by words, when you take this argument to be negative, the logarithm develops an imaginary part, which scales with pi, right? The imaginary part is pi. And after you take the derivative with respect to the energy, you get some period. You get a period that depends on pi. So that's exactly you get 2 pi. You get the period of a circular orbit. So yeah, so basically this allows you to get all possible observables between these two different regimes. Yeah. So yeah, so this is to say that, for example, in the inspiral problem in gravity, what you can do is, it turns out, because we have so many good techniques of computing Feynman diagrams today, it's actually easier to compute Feynman diagrams to very high order and talk about this exponent and then describe these classical observables. So these classical observables that have been computed to very high order that are helpful in the inspiral problem in LIGO have actually been computed using Feynman diagrams, because we got so good. We understood that it actually exponentiates, and from this exponent, I can extract some classical action and I can compute some classical observables. Okay. Yeah, but unfortunately, this process of continuation is like the biggest open problem right now is that it stops at order g to the 4, when g Newton is like power 4. You get a function which is not analytic, and you cannot continue. You cannot do this continuation. So that's a big open problem. And I'm gonna try to get to there just to show the diagram in which it happens. Yeah. So let me just get to QFT and get to the positronium case. So I think it was a bit ambitious what I wanted to do. So if I do. So in QED, okay, actually, before we do positronium, let's do QED corrections to hydrogen spectrum. So in this case, my amplitude in QED will have to be a sum of all possible diagrams, right? So I have this diagram, and I have this other diagram, which we talked about. But now I have other diagrams. I have, for example, this diagram here. This is the vacuum polarization diagram. I also have the triangle correction diagram. So I have something like this. Okay. So I have also the crossed box. All of these sum together. So I have a whole bunch of diagrams. Now what I can do is to reinterpret this expansion in terms of some expansion of some V, which connects with itself in terms of these bubble diagrams. Okay. Okay, so this is a Born series in quantum mechanics, right? And I can make this more precise by making the Green's function here, the two particle cut, to be relativistic, right? So because all of these are relativistic, this is not just the hydrogen atom, it's not just quantum mechanics. I must make this consistent. I must make that this V has no two particle cut, has no imaginary part, and all of it is absorbed in some connection, right? And once I make this statement precise, which I don't have to make, I don't have time to make. Once I make this statement precise, I can match these two expansions, right? So by matching these two expansions, I can read off this V from this expansion, right? So when I do that, for example, I would say that this V to leading order is given by this, and then this guy will be related to this box diagram. And this triple V would be the ladder diagrams that we described in the hydrogen atom. So in other words, this V would absorb this guy, and this diagram is simply the one that gives you the Coulomb potential, right? Once I have this V, I know that the amplitude resums to some kind of geometric series. I can use this potentially, some kind of Schrodinger equation. I can extract the energy levels once I do this matching procedure. So this is to describe a more systematic way of doing what we were doing before, right? So just noting that this expansion, I can reorganize the expansion in this form. So this V will absorb this diagram, but it will also absorb this diagram. It will also absorb this diagram. And in fact, you'll see that it does not absorb these cross ladders once you make this precise. Okay, so your potential gets corrections. You have this Coulomb piece, but you have also vacuum polarization piece you also have this other piece, and then you can use it to correct the energy levels of the hydrogen atom, and this will lead you, for example, these two contribute to the famous lamp shift, right? That people computed in the 50s. Even though they computed in a different way. So this approach was done. It's in this very nice paper, which is Todorov, 1970s. And actually, this was rediscovered today. Like in a few years ago, like I mean, around 10 years ago, this is when people started discussing about gravity waves using amplitudes. This approach was rediscovered, okay? But this was already done in the 70s, exactly to tackle these corrections to energy levels. Okay? Although this paper is quite obscure. So this, if you account for this will give you exactly this lamp shift correction, this hyperfine splitting of the hydrogen atom. So now I want to describe something which I think is very interesting, which is what is different for positronium. So if I don't do hydrogen atom, I do positronium. So for positronium, there are more diagrams. It's not just this one. So for positronium, there's another diagram. Let me erase this one. Because for the proton and the electron, these lines are different. These lines are completely different. One is the electron, the other is the proton. But for positronium, these are electron and positron. So they are the same lines, except they go with different arrows. Right. So there's another diagram you can draw, which is basically flipping this guy. So there's a diagram which is this one. Here. Okay. This diagram here. I can draw this diagram for positronium. I cannot draw it for hydrogen. So I mean positron, I mean scattering of an electron and a positron. So what is different about this diagram? Does anyone know? What is special about this diagram compared to the other ones? So my first question would be, does this diagram go into V or does it go here? So the diagram cannot come here because this is massive exchanges. So this is this guy absorbs this one. This one is photons, so it has to come to V. So this will go absorbed into the potential. Right? So this goes into V. Now, the crucial thing is that you have a 2-photon exchange in the S channel. So this means that this guy, this potential, has some imaginary part because I have the photons here. So if I scatter this object, this electron and positron, even if they have some tiny energy, they will produce 2 photons. There's going to be an imaginary part here, right? So this means that the potential will have an imaginary part, right? And the formula for this diagram, like in this regime, like in this regime where there's some non-relativistic regime, right, that we're talking, this effectively has this formula. It's given by e to the 4, the mass, and then the logarithm with minus the energy. So for any positive energy, so actually I mean energy here, I mean by the sum of the masses, so 2 times the mass plus some binding energy, right? So any positive energy will make this guy become imaginary. So this will develop some imaginary part given by I pi e to the 4 mass of electron square. Okay. So this will be the V. And well, now you can compute how this changes the energy levels. This sends the energy levels to the lower half plane. It makes them complex, so it makes them unstable. So this explains why positron is unstable, and we can actually compute the decay rate with this V. So this gives you the right decay rate, and you can find this like in Landau-Lifshitz, deep inside the book. You find this analysis. Okay, so yeah. So questions here?
I have a question. When you have an electron and a positron and you measure them, you measure that exact cut, so the production of two photons, you always only see a peak in the energy of the photons at the masses of the electron and the positron.
Yeah, you scatter them into two photons. Yeah.
Yeah. How is that apparent in the amplitude? Why can't you see some kinetic energy on the photon? So the energy of it's always just a peak on the masses of the electrons and the positron. How is that apparent from the amplitude?
Yeah, but well, no. Wait.
I'm saying an experimental fact that I see. And
No, but it's not the peak. Only if they are at rest. Right? If they send them with some energy.
no, the thing that I noticed and it was told me and then I saw it was that the process of losing kinetic energy was preferable until they were both at rest and they would decay into two photons.
Yeah.
And how does one see that preference? Or
well, I guess the logarithm, let me see I mean clearly the logarithm will. Well, actually, I don't know. I mean, you have to compare the amplitude. I mean, one thing is
compare the amplitude.
Yeah. So the one process is the electron and the positron into two photons, right?
Yes.
I'm talking electron and positron into electron and positron.
Mm-hmm.
The fact that you're talking about that they can decay and they can annihilate is included in the fact that this diagram exists and there is an imaginary part. So
yes.
what I think that yeah, indeed, the fact that they decay is already included in the fact that the amplitude has this imaginary part and is included in the fact that the energy levels become imaginary. This is how everything is connected, right? I mean, just that.
Yeah.
So yeah, I mean, I don't know if that's the question you were asking.
It is. It's how one compares that the diagram that will reproduce the decay of an electron and a positron with the exchange of a photon so that they lose kinetic energy, so that in the end that they always decay into two photons with always the energy at the level of the rest mass of the positron.
Yeah, this is some dynamical process that I don't know. Maybe the amplitudes can help you decide it, but I don't see.
Yeah. Maybe it was clear from the perspective when maybe one just has to compare the two of them and to see.
Yeah, one probably want to compare the two amplitudes. Yeah.
But yeah,
Yeah.
it was just a funny fact that I observed actually.
Yeah. Yeah. So let me just finish. Sorry, I'm a bit over time. Let me just finish by saying how does this translate to gravity, classical gravity in black holes? Just very quickly. I'm just gonna draw some diagrams. Okay. So when you do gravity, there's one key difference. One is that the graviton can self-interact. Okay, there's this 3-point coupling. So if I redo everything that I want, I did, so I compute the amplitude. So you're going to have the same graviton exchange, but you also have the correction. Okay. You also have the box, but you have these other diagrams, which get lumped into the potential. So this guy will give you G over R, and this will give you a correction G squared over R squared. Now, this correction is exactly what you get from expanding the Schwarzschild metric at this order, and this is responsible for the perihelion precession of Mercury. I didn't have time to derive it, but in diagrams, this diagram is the one that's responsible for Mercury perihelion precession. Okay, so that's cool. You don't see that in Coulomb, you see that in gravity. Okay. Now, another thing is that in gravity, you have a lot of interesting things that happen because of this coupling. The other is like, for example, you can ask, where are black holes? Like, so I get this term, which is G squared expansion of the Schwarzschild metric. Black holes arise when you consider all types of diagrams that are of this form. which have one exchange. There's one triangle. There's another one which branches out. There's another one which does the same story, but with 4. So all of these type of 3 diagrams which exist in gravity, they resum to give you the Schwarzschild metric. So this was the result of actually this year that people actually proved this. It's a paper by Damgaard and all, which I don't remember the other author, okay, for example. But it's still open to do this, like for curves, the black hole, etc. We don't know. Now, another thing I want to say is you also have diagrams which are at high orders, which have the following form, like something like this. And then you have, for example, another graviton being emitted here in the middle. Okay, so this gives you similar story to the positronium. This diagram does not get grouped into the 2-particle exchange. This has to go to the potential because there's not a strict 2-particle cut. There's another graviton gets emitted. So this is gravity waves, precisely. We can compute with this diagram, we compute how orbits emit radiation and they decay, for example. And finally, because I'm out of time, there's another, the final, so this is at order g cubed, okay? We get radiation at order g cubed. And finally, the interesting diagram where that stopped all these amplitudes methods in its tracks, and it's a big open problem, which for me is I think one of the most interesting open problems, is that at g to the 4, you have so this diagram, you also have another diagram like this, okay? At g cubed. It's a similar one, where I have like some graviton here. Similar story. I also have a 2-particle cut, graviton. They are both the same. But now, at order g to the 4, you can draw this diagram here. So this is very high order, g to the 4. To do this, you do the same diagram, but now you add another graviton. Okay? So this is a diagram that only, well, sorry, did I screw up? Yeah, it's this, sorry, g to the 4. So I have square root g, and this is g to the 4, okay? So it's this diagram, but you add this leg here of graviton. So this is only in GR. This diagram only exists in GR, right? So what's special about this diagram? This diagram, it has to go into the potential, as I explained, as we see here. But this diagram does not allow an analytic continuation. This diagram does not allow it to access the bound regime. So this one fails. So, and then there's a big, almost philosophical question here, which is: are you an S matrix believer or are you not an S matrix believer? If you are an S matrix believer, you believe that the S matrix contains all information about bound states and scattering. So therefore, you should be able to, if you have the whole set of diagrams, you should be able to analytically continue and find information about the bound orbits, right? But it may be possible that this diagram alone does not give you the right analytic continuation. Maybe you have to resum a subclass of diagrams which give you the right analytic continuation. And now I can conjecture a bit. I think the right class of diagrams is the diagrams of this form, where you add a whole ladder of gravitons here. Okay, so this is called the tail effect, which gives you, so the fact that it exists, this exchange, this just tells you that the graviton you emitted gets pulled back again by gravity, and then, so it's somehow the information that this graviton is actually not free, is actually bound together, is kind of what people understand is the problem. So maybe you have to say that, let's consider a whole class of diagrams here, which resum into something that looks better and I can analytically continue. I don't know. So let me just finish here. Sorry. Thanks.
Thank you. Okay, thank you. Very good talk. So are there any more questions? Yeah. So actually, regarding that the rig down process that you described, so I have a question that I'm not sure if you approached it and I just didn't get it, but so if you so in the hydrogen atom, for example, you have electron and the proton, and there are exchanges that you can describe by a Feynman diagram. In the ring down process, so after the merger, you have one black hole.
Yeah.
And then if you were to draw Feynman diagrams, it would be what, the black hole interacting with something else, or like the two black holes that have already merged.
Yeah, that's a good question. It's very hard to understand what happens in the merger, right? Because in a QFT perspective, you have two particles going to one, right?
Yeah.
It's like there's a process of two bodies decaying into one body,
Yes.
which has slower mass, smaller mass. Yeah, I mean, what happens is in the ring down, what you have is instead of one of the lines here is a graviton. So now you can consider the process of a black hole and the graviton scattering on top of it. Right, just without, let's not go to ring down. Consider just a case where I have a black hole and the graviton scattering. That's just scattering of a gravity wave on the black hole. But now I know that if I do the right things, I can analytically continue to the negative energies. So I can describe the bound process of this graviton to the black hole. So this is exactly what happens in the ring down. So if you're smart enough, which people have not been able to do yet, you would be able to compute the quasi-normal modes from this S matrix. So the quasi-normal modes of the black hole, which are these ring downs spectrum, these energies, these frequencies, comes as poles of the amplitude. They will come up as just like in the hydrogen spectrum where I have the energy level, the quasi-normal modes will appear as poles. Well, this is if you are an S matrix believer. Yeah.
Okay. Thanks.
Next question. How does the hydrogen spectrum appear in a complex J plane?
Yeah, so it appears as Reggie poles, exactly. So there's going to be Reggie poles, so you can do this. One plus J alpha E, one plus L alpha E. So I can solve when this is 0 or when this is a negative integer, and I can solve for L now.
Yes.
Instead of solving for the energy, I solve for L. This will give you Reggie poles. And this is exactly like it just gives you Reggie poles, which will be somewhere in the complex plane. And then when you take the energies to be exactly at the spectrum, they will cross an integer, which is what we expect. When the Reggie trajectory becomes an actual physical state, it becomes an integer. So
But the Reggie trajectory will be a family of poles. Are these poles like they all have the same angular momentum? Are all the orbitals of the hydrogen atom with the same angular momentum? Can I think it a bit like that? Or can I find a family of orbitals that are connected?
Yeah, this is all, you could say this is all the same Reggie trajectory. The hydrogen atom spectrum is all connected with the same Reggie trajectory.
Oh, it's only one Reggie trajectory that connects all the orbitals.
No, sorry, no, there's different. No, there's different integers. Sorry, it's not true. Wait 1 second. Yeah, I think you could say they are connected. Wait. Well, no. Actually, there's different families. Yeah, there's different families because for each of these negative integers, you have one family, and then this tells you how, for example, the state n equals 2, how many spins it has. So like
exactly. So it aligns the orbitals.
It connects all the orbitals. Yes, exactly.
That's very cool. That's very cool.
Yeah. So yeah, I mean this is what inspired people also to think about these Reggie trajectories for QCD. For mesons. So like that's why we think all these hadrons or these mesons are all connected by the same Reggie trajectory, which is very simple. It's linear.
Mm-hmm. Mm-hmm.
This is more complicated than QCD, the formula, right? What we expect.
Yes. Okay.
Yeah, I mean, sorry, there was many things that was impossible to cover. Like there's other regimes. There's a wave regime, classical waves. I didn't go into all of that. So there's many things that you can do. And, I mean, I decided to show this. Yeah.
Okay, very cool. Now let's thank Miguel again then.